Thanks a lot. A great pleasure to be here to present the work I did during my PhD, which is unrelated to mostly the thing I do for Julia, the Julia community in general. But I'm happy to be able to show it still because I'm using Julia extensively in this project. So the main thing in the title is called Coulomb explosion, and what it is actually quite simple. Is that if you take a very big laser, the one that have been used for this experiment is like 3 kilometers long. I can explain later why. And you use it to shoot a molecule. Well, the result is very simple. The molecule explodes, and we can collect the fragments, and it gives us a lot of data. And the main question of my PhD is, what can we do with this data? What can we tell about the molecule before it just got blown up, essentially? So the molecule we are using and that I will present is iodopyridine that you can see here. It's quite simple. What it is does not really matter. I will speak in a bit more general term as this specific thing. So the data we are collecting look a bit like this. So we don't actually measure the fragment per se. We measure the velocity they have when they leave the explosion. And we can know which element they have. And it gives you this kind of maps where you see, okay, I have some distribution of velocities for my fragments. And the cool thing is that in the molecule at the beginning, there's like 5 carbon atoms. And at the end, you see 5 blobs in the data. Yay, incredible. We can say we have kind of atomic resolution. We can see each atom specifically. Nice. That was the easy part. What we noticed later by looking at the data a bit more in depth is that the measurement we made, the velocity of the fragment, they are not independent from each other. What I'm showing here is that what happened when you actually beam the data on the velocity of one of the fragments. Here it's beamed as a fragment of this purple fragment here, iodine. And what you see is that when iodine is fast, big velocity, essentially all the other fragments are also fast. And when iodine is slow, everything else is slow, which simply shows that there is some level of correlation between how things are moving or how things are measured. And we ask a very simple question. We ask, okay, how can we find all interesting correlation in that kind of data? And that's where the problem begins. Because if we had the perfect data, beautiful things as we have in simulation, we measure all fragments all the time very well, it's a trivial question. It's very easy to do. Unfortunately, I happen to be working with experimentalists, and reality is a bit harder than that for multiple reasons. First of all, we don't measure everything every time. The idea is to blow up one molecule after the other and look at the fragments. In average, like half of them are measured. Not very nice. More than that, we had what we call the loss of identity. When you measure a carbon atom, you don't know which one you measured. You know it's carbon. That's it. And although I say it's not so easy to control single molecules, so they are actually randomly oriented. So not only you don't know exactly what you measure, but you don't know in which direction it is relative to the rest, because it was in the gaze phase and just randomly oriented. And there is some low density background, and that's a bit unfortunate. So for all this reason, the data is challenging, and we were like, okay, what is the simplest thing we can do to show correlation? And it is to fit a Gaussian to the data, a high dimensional Gaussian. We thought it would be easy, and it was not. Our strategy is very simple. We say, as I put in the title, we say, let's try to brute force it. So we have our experimental data. Nice. We have a Gaussian model. Cool. We'll simply do the fit in a very simple way. We define a loss function. We compare them. If it's converged, we say, cool, we are finished. And if it's not converged, we do a gradient descent. We compute the gradient. We use a standard optimization algorithm and move forward. And that would work perfectly. It would be a terrible way to do it if we had the perfect data, but it would work. In our case, we decided to go a bit indirectly, just to be able to deal with all the problem in the data. So the first things we do is that we need a guess. So we need a guess for the model. fine. But to be able to define this guess, we need to get rid of the background. And that we do by doing some filtering. And then to get rid of the fact that the molecule is randomly oriented, we convert the velocity to scalar product because scalar products are independent of orientation. Nice. Then we go one step further saying, okay, we want to be independent of what we are not measuring. And you can actually do that by computing statistical moment like mean, standard deviation, and higher moment to do that. And we can do it from both the model and the experiment, so we can later compare them. And then there is a little trick just to get rid of the invariance to the unknown quantity. Now you may ask, this is a Julia conference, where is Julia entering in all that? And the answer is everywhere. So first, to filter out the low density region, I will just walk through all the package I used. That was the point of the presentation. To get rid of the low density region, I had to use clustering, the nearest neighbor, and other things to identify low density and get rid of it. Then I use Gaussian mixture for Gaussian mixture, very, very reasonable. To be able to compute this statistical moment, there is this very cool package called Cumulant that do exactly what I needed, but not for me. So I just use it for testing purpose. And then the rest, memoization, online stat, and Tulio, they are all things you can use to get better performances. Especially Tulio, I used it to define new specific rules for very specific matrix operation, because my operation had a very specific form. And then to do the average over things that are equivalent, I use combinatorics. To compare the experiment and the simulation, I have made extensive use of unitful, because of course no one uses the same units all the time. And finally, to do the final kind of analysis and put everything together, I use multivariate stats and Mackie. And by putting all of that together, for computing the gradient, I use Zygote, because it's what was best at the time, and to do the optimization Optim. And so by putting everything together, we were able to do this very last step that says, okay, now we have found correlation in the experiment. We just happen to have simulation that shows the same correlation. And from the simulation, we can link that to the quantum property of the molecule. And by putting everything together, we were able to say, okay, it really looks like in the experiment, we have measured this quantum fluctuation. We are kind of the first to do it to this level. And that's why we could publish that. And we are very happy about it. And that's really how Julia helped me finish my PhD. Thank you very much for your attention. And if you have any question.
Do you have some questions? Yes. Wait for me.
Thank you for the interesting talk. So I have two small questions.
Yeah?
How do you interpret the parameters of the distributions that you found, particularly the variance? And my second question is, have you tried any compressed sensing methods on this data?
Can you come again with the second part?
Have you tried any compressed sensing methods?
No. Okay. So I can say a bit more about the second part. The problem is that I'm trained as a physicist in a physicist group, so there was kind of little understanding of the general field of data analysis and so on. And for the first thing, the way we interpret, mostly we are interested in the parameter we're interested in is the covariance matrix, and that we can link to the really quantum fluctuation. It's a mathematical trick, but they have the same kind of structure. And that's how we interpret. We say, okay, we have this fluctuation, they are causing this, and that's what we can actually show that they are strongly, one is caused by the other in the simulation, and just we find them in the experiment separately.